in order to work out how fast you need to hula hoop in order to keep it from falling down your body, you maybe need to understand a bit how the hoop is moving. Now what you could do is look at every single point on the hula hoop and work out equations and things like that. That would be horribly complicated. So there is a simpler way. Now often in physics, when you're looking at the movement of an object, you don't actually have to look at the whole movement of the object. What you do is you say the mass is all concentrated at the centre of the object, at a point called the centre of mass, which is right in the middle, and then you only have to look at that. So that could be helpful. Not true in all cases, as we shall see. So if we're looking at the hula hoop going around here, the centre of mass is doing a circle, which is kind of round, sort of round there. However, that's not the whole story, because if it was just about the centre of mass, if I was doing this, the hula hoop would be still. Well, if I was doing it properly, this is a hoop move called an isolation, where you move the hoop but it looks like it's staying still. Clearly it's not staying still, so something else is happening. It also doesn't explain this. Let's try this. Come back. It came back. And this is something else we have to consider, which is spin. So this is pure spin, and you can see that the centre of mass is not really moving, but the hoop is moving, so it's spinning around its centre of mass. If you were to do that in a no gravity middle of space thing, if a hoop was spinning around its centre of mass, it would actually, if the centre of mass was staying still, the centre of mass started off staying still, it would remain staying still, but the hoop would be spinning around the centre of mass. If the centre of mass was moving and the hoop was spinning, the hoop would continue to spin in the same way, and the centre of mass would continue to follow the rule that it would move in the same direction and the same speed forever and ever until force was applied to it. Anyway, so if we're trying to look at the movement of the hoop, if we just look at the movement of the centre of mass, if I kind of do a circle like this, that's roughly centre of mass is moving in a circle. If I go like this, again, centre of mass is moving in a circle, but it's not the same because you've got spin. So to work out the movement of each point in the hula hoop, what you can do is you can add together the movement of the centre of mass and the movement of the spin. Now the most interesting thing, well, think about car wheels. That's quite interesting, because what you have here with a car wheel, I don't know if you can see this, is that the centre of mass is moving along at the same speed as the car, but the wheel is also spinning this way, and that means that the spinning part, the bottom of the hoop, is actually going in the opposite direction to the car. However, if you add it together, so centre of mass is moving, but there's also this spin, that means at the bottom of the hoop, at the bottom of the wheel, they cancel each other out. So actually, in a car, a moving car, there's always a point on the wheel which is absolutely stationary, and this is how you get the grip onto the road. You can tell in a car if you're sliding, because that's when that bit of the wheel touching the floor is not still, it's moving. So if the wheels, for example, get locked, or you're on something very slippy, then you lose control in that case. The top of the wheel, on the other hand, if it's going along like that, the centre of mass is moving in that direction. The top of the wheel, the spin is also moving in that direction. So actually, the top of the wheel in a car is moving at twice the speed that the car is moving. Now, and this has to be true if you're going to get the grip, if you're going to get a rolling motion. And it's the same when you've got hula hoop. So the bit, in this case, the centre of mass is doing a circle, but you've also got a spin. So, if we look at this, the outside bat is spinning in the same direction as the centre of mass is moving, so it's actually twice the speed of the centre of mass. The bit in contact with your body is actually moving in the opposite direction, so that it's still. This is also a useful thing to remember if you're tossing the hoop in the air. I hope I won't damage my ceiling. So if you put some spin on it, so if I'm spinning around this way, when the hoop comes down, so that slide is going up, so that slide, the spin will be going up on this side still, and the hoop, centre of mass will be moving down. So if you're throwing something up with a bit of spin, that didn't work, but you can't, it's better if you catch it on the side where the spin is going down. And of course this old favourite, what's happening here is when I toss it, when it's moving through the air, its motion is determined just by the centre of mass, but when it touches the ground, then it starts rolling, and that's determined by the spin. So you can either get it to come back to you if the spin is sort of moving towards you. So in that case, let's see. So if the spin is in this direction, if you send it off, it will come back. If you send it off with the spin in the opposite direction, it will roll away. So that's kind of how the hula hoop moves. But the important principle is that the outer edge is moving at twice the speed of the centre of mass. I realise I haven't really defined what I mean by the speed that I'm hula hooping. Well, there's different ways you can look at it, but I think the way that you feel when you're hula hooping about speed is the speed where the hula hoop feels like it's gone round and got back to the start. So the time between, say, it hits your tummy and then it hits your tummy for the next time. And this is very important for timing lots of moves, because if you want to stick your hands in, you have to get that right to be able to do stuff like that. Or if you're going around your legs and you want to get your leg out, you need to get the right timing so that you've got a gap in the hoop to do things. So if you're looking at circular motion, it's kind of the frequency of the hoop, really. That's not a very good way of putting it, but never mind. So, but if we think about the speed that the hoop is actually going, so if we think about this, the time it takes, let's call it the time it takes for the hoop to go around. How fast are the different bits of the hoop travelling? If we go back to Piggy, Piggy's gone. That's Piggy. If you look at Piggy travelling in a circle, if he's travelling in a little circle, he's going to be going slower if he takes the same time as he would take to travel around a great big circle. Oh, he's gone flying again. If you look at hand hooping, now, I don't know if you can see this, but the outside, as I said, the outside of the hoop is travelling really quite fast, so that's probably blurry in the film. Whereas you can probably actually see the colours close to my hands quite clearly because they're going quite slowly. But what effect does size have? If you've got the outside of the hoop, we want to have it fast enough so that it spins up and it doesn't fall down. It's the speed at which the outside of the hoop, the fastest part of the hoop, is travelling, which determines that. So basically, the bigger the circle that's making, so the bigger the hoop, the slower you can hoop. So let me illustrate that. Let's do a great big hoop, and I'll see how slow I can go before it falls down. Oh, my kitchen isn't big enough. 1, 2, 3, 4, 5. So that's about how slow I should time it really. If we go to kind of medium hoop, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can't do it as slowly as this one before it falling down. I have a really little hoop. This is a 30-inch hoop. This is the limit at which I can hoop. 2, 3, 4, 5, 6, 7, 9. And a really tiny hoop. The 24-inch hoop. This, no adult, I don't believe any adult can hoop with this. So basically, the bigger the hoop, the slower you can hoop, and usually the easier it is, though it depends what you're used to. So the other thing, that was good, it also depends on the size of the part you're hooping around. So I can twirl this around my hand, no problem at all. These you can use for hand hooping, because my hand is much smaller. And I don't completely understand. I know that if you're smaller, you can work out that actually the circle the hoop makes is bigger, but there's something else which I don't understand that's going on there. But so basically, from what I've talked about, to design a hoop which is easier to hoop with, firstly, put grippy stuff on it, wear clothes which are not too slippy as well, and secondly, get yourself a big hoop. I still haven't explained really how to hula hoop and how to keep the hoop from falling down, how to make it go fast enough. But what you're basically doing, if you think about a roundabout or something like that, to keep it going at a good speed, I've got a squeaky floorboard here, you just give it a shove. And you can be standing on one side of it, and you can keep giving it a shove, and it will start going around faster. You don't have to do it in all the directions, because the force, in the case of a roundabout, the post holding it in the middle, in the case of a hula hoop, me standing here, means that you're applying, you don't need to apply force in all directions, but you need to give the hoop a helping hand. So often people find you don't have to go in a circle. People often do strange twisty things when they're trying to hoop. You don't need to. You don't need to twist your hoops at all. You could either do a kind of circle. The important thing is the timing. So what you're doing is when the hoop's in contact with you, you're just moving it a little further, a little faster in the same direction it was moving anyway, and that will give it a little shove and keep it moving fast enough to keep going. If you stop moving, as I say, it will spiral down the body. Sometimes, if you get it going fast enough, you can get it back up again. So, you can either go side to side, or backwards and forwards, and hit everything in your kitchen, or you can do a kind of circle. And all of them will work, just as long as you keep the movement flat in the plane of direction you want the hula hoop to go in. If you don't want the hula hoop to be flat-ish, because it's always going to droop because the gravity's always pulling it down, then you can explore with jumping up and down. You see, it's no longer in the plane. So I'm kind of doing, now I'm going up and down, so the hoop's direction has changed as well, because I'm giving it a little shove in the up and down direction. So when you give it a shove, always has to be in the plane you want it to move in, but it doesn't have to be all every direction. So that's kind of how to hula hoop. What's the last thing?